Question 2. So the goal of question 2 is to establish the Taylor series expansion for the function sine of x. And the interval here is the entire real line. And we're going to center it around the point a equals to 0. So from lecture, we learned that if f is of class ck, so ck means that you have up to the kth derivative of f, and all the derivatives will be continuous, right? That's ck. So if f is of class ck on an interval I, and we center around a inside of the interval, then we have that our function fx can be expressed as some px plus some r of x, where px and rx are, as you can see here, and that's something we should have already done in lecture. So question A is to ask, for any fixed constant c greater than 0, prove that c to the power k divided by k factorial will go to 0 as k goes to infinity. And your instructor has a hint, which I won't use directly. I'll use a modified version of that hint. So let d be equal to the ceiling of c. So this is, if we take c and round it up to the nearest integer, that's what d is. Then obviously we will have this expression. So then this expression is true. That's just common sense. So now we consider what happens when k is greater than d. So when k is greater than d, what happens? We have that d to the power k divided by k factorial is equal to d over 1, d over 2, dot, 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 d over d, and it will keep going. So d over d plus 1, d over d plus 2, dot, 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 and that's going to be d over d plus k minus d. Okay. So now we observe that for this portion, each term is less than or equal to d over d plus 1. And that's just obvious because the denominators are continually getting larger. And we have k minus d amount of such terms. For the portion on the left, this portion, that portion, that's just d to the power d over d factorial. So overall what we have is d to the power d over d factorial times d over d plus 1 to the power k minus d. And remember, k is strictly greater than d, so this term here makes sense. So because d over d plus 1 is strictly between 0 and 1, as the exponent gets larger and larger, the term will get closer and closer to 0. So let me write that out. So observe that the limit as k goes to infinity of this guy is equal to 0 because it's strictly between 0 and 1. So overall, from before, we have that 0 is less than or equal to c to the power k over k factorial. That's less than or equal to d to the power k over k factorial. And then we saw that d to the power k over k factorial is less than or equal to d to the power d over d factorial times d over d plus 1 to the power k minus d. So we know that this portion, it goes to 0 as k goes to infinity. This portion here is just a scalar. It's just a scalar. So overall, as k goes to infinity, we see that c to the power k over k factorial goes to 0 by squeeze theorem. And that's it for question 2a.